Here is part 2 on the lectures for Maxwell's equations. What are the implications of Maxwell's equations? Well, let's set up the following situation involving a specific type of wire called an antenna. So I have right here a generator which generates an alternating current. Let's say at this particular moment the current is flowing upwards through the wire in this direction, and also at this moment the current is decreasing in magnitude. This then means that on the right-hand side of the board here, I'm not bothering to draw it on the left, on the right-hand side of the board here, we would have, first of all, from Ampere's law, the magnetic field B circulating into the board at this moment in this direction. And then from Faraday's law, we would have an induced circular electric field, which then circulates like so in my diagram. This is all assuming at this moment that the current's magnitude is decreasing as a function of time. Okay, now recall that the fields themselves have an energy density. So then therefore, what's going to happen a half a period later when the current is moving in the opposite direction? Well, these fields just can't disappear, because if they disappeared, that would imply that energy was destroyed. Instead, the following must occur. Okay, now over here on the left-hand side, this is a half a period later, notice that the current I is flowing in the opposite direction. So once again, on just the right-hand side of the wire here, I drew what the fields look like at this moment. We have the electric field here in red, and then the magnetic field here in black. And then this right here is describing the fields from earlier, one half period earlier from the top board. Those fields begin to propagate in this direction. Once again, the fields cannot disappear, because if they did, that would imply that the energy was destroyed. The field lines must connect upon themselves, because if they don't, once again, that would imply that energy has been destroyed. The fields themselves cannot instantaneously fill all of space out to infinity. Therefore, the fields themselves must propagate through space at a finite speed. Propagate through space at a finite speed. Maxwell is making a big leap here. Now, recall the Newtonian picture of gravity. The Newtonian picture of gravity is that the force of gravity occurs instantaneously throughout the entire universe. Maxwell is assuming differently for the force of electromagnetism, and the reason why he's doing so is because we know that the fields themselves have an energy density associated with them. Therefore, they cannot fill all of space instantaneously. They have to propagate through space at a finite speed. The fields cannot disappear, and the field lines must connect upon themselves. Now, very far from the antenna, these fields here look more and more like straight lines. That's what I've drawn here on the far right-hand board, where the direction of the propagation of the fields themselves is to the right-hand side of the expression. So once again, Maxwell here is going far beyond the Newtonian picture of gravity. This is a much deeper understanding as to what is happening here now with the force of electromagnetism. Okay, now what actually happens to Maxwell's equations in a situation such as this? In other words, a situation where you have a region of space where there are fields present, but there are no charges, nor are there any currents. We just have the fields themselves. What happens in Maxwell's equations when that occurs? Okay, now, Maxwell's equations in empty space with only fields present. Notice the symmetry of the expressions. First of all, Gauss's law. First for electricity. And now for magnetism. Notice the zero here because there is no charge in the empty space. Okay, now for magnetism. Okay, and then we have Ampere's law. Now when I write Ampere's law here, there's no current enclosed. We only have the displacement current term, which if you recall, is the following expression. A changing electric flux induces a magnetic field. But then we also have Faraday's law. Oops, this line integral here involving electric fields. Like so, where a changing magnetic flux then induces an electric field. Once again, notice the symmetry. The expressions can be combined together using some calculus, quite frankly, that you guys haven't seen yet. It's covered in the third semester of calculus. It's a little bit beyond the scope of this course. But when you do combine the expressions together, you end up with a partial differential equation. The equations can be combined together, resulting in a partial differential equation. That partial differential equation is describing this region of empty space where we only have fields present. The solution to that partial differential equation is a propagating cosine curve. Okay, what is a propagating cosine curve? What I want you to do right now is pause this lecture and then take a look at the screencast that I've posted for you in today's folder called the Simple Periodic Wave Screencast. So take a look at that now. Okay, now that you've seen that screencast, a propagating cosine curve is what is called a simple periodic wave. Let me do some erasing here. A term emerges from the partial differential equation and its solution, the solution being a simple periodic wave, a propagating cosine curve. The term that emerges out of the solution to the partial differential equation is the following. This term here. So what is this term? Well, we have here are two constants. Okay, first of all, we have the permittivity of free space going all the way back to Gauss's law in chapter 22. Recall that the permittivity of free space basically describes the following. It describes the magnitude of an electric field in a vacuum. It's a fundamental constant. And when I introduce that constant to you in class, you sit there at your desk and you stare at me and you go, okay. And then a little while later, about a month or so later, when we eventually get to chapter 28 with Ampere's law, I introduce you to another fundamental constant. This guy right here, the permeability of free space, which describes the magnitude of a magnetic field in a vacuum. It's once again a fundamental constant. I introduce the constant to you, you sit there in your chair and you stare at me and you say, okay, and then we move on from there. But once again, from the solution of the partial differential equation that results when you combine Maxwell's equations together, the following term emerges. Okay, now let's look a little bit more closely at that term. Specifically, let's take a look at the units first. Let's do a little bit of detailed dimensional analysis here. Okay, so first of all, recall epsilon naught. Okay, it's been a little while since we've seen it, but back from chapter 22, the units of epsilon naught, the permittivity of free space, are the following. Coulomb squared per Newton meter squared. And then we have here the permeability of free space from Ampere's law. From Ampere's law, the units of the permeability of free space are the following. It is Tesla meter per ampere. I have to think about it for just a moment. Tesla meter per ampere. Let's go ahead and take these units and plug them down here underneath the radical sign. Okay, so first of all, I have the permeability, like so. And then next, the permittivity, like so. Okay, now the first thing to do here is to actually write a Tesla in terms of everything else. Let's go all the way back to chapter 27 for just a moment. Recall from chapter 27 the following force expression. IL cross B, just writing it in terms of a magnitude, we'll just write it as ILB. So right here is a Newton, right here is an ampere, right here is a meter, and then right here is a Tesla, like so. So a Tesla is equal to a Newton per ampere meter, like so. Let's go ahead and take that and plug it into here, and then when I do, a bunch of stuff begins to cancel out. And let me do that up here. Okay, so now we have a Tesla, which is a Newton per ampere meter, multiplying it by a meter, dividing it then by an ampere, and then right here is Coulomb squared still per Newton meter squared, like so. Okay, at this point some stuff begins to cancel out. Let's go ahead and start to simplify. All right, so I have meter, first of all, canceling with meter, Newton canceling with Newton, like so. And then I have right here an ampere squared, Coulomb squared over meters squared. Once again, let's start to rewrite this. Like so. So here's a Coulomb squared per ampere squared times meter squared. Now an ampere is a Coulomb per second. So we have here Coulomb squared divided by Coulomb per second squared. So Coulomb squared per second squared, and then times meter squared. See what's happening here? The Coulomb squared cancels out, like so. Let's go ahead now and rearrange this expression like so. Take a look at that carefully, and then take the square root. It's meters per second. It's a speed. It's the speed of this propagation. Okay, now what is the actual number? Okay, so now we have the numbers. Okay, first of all, the permittivity. Epsilon naught, it's been a while since we've seen it, 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay, and then we have the permeability. 4 pi times 10 to the minus 7 Tesla meter per ampere. Okay, now we always write it as 4 pi because it's easy to remember. But let me go ahead and write that as a decimal instead. So 4 times pi is about 12.57, give or take. So let me rewrite that like so. Like so. And now let's go ahead and plug these guys in. All right, so 12.57 times 10 to the minus 7. And we'll multiply that by 8.85 times 10 to the minus 12. And then let's see what we obtain. All right, so 12.57 times 10 to the minus 7. Multiply that by 8.85 times 10 to the minus 12. Okay, take the square root of all of that. And then put it all up into the numerator. And then I end up with this. Recognize that number? You should. It's the speed of light. The speed of light had been measured prior to the work of Maxwell. It was actually measured very accurately as early as the mid-19th century. So then therefore, Maxwell, what he has done here is he has derived the speed of light. Just imagine his reaction. He actually later recounted to his wife what his reaction was as he labored at his desk one evening in Scotland, where he actually derived the speed of light. He sat there stunned at his desk, just staring at his page, written more or less like so, for an hour, because he realized that he was the first human being ever to understand exactly what light is. Light is an electromagnetic wave. Now at this point, what I want you to do is take a look at the next screencast video that is in today's folder. And I also want you to take a look at the electromagnetic spectrum lecture that I've posted for you as well. I actually wrote up that screencast and that lecture for the other classes, physics, honors physics, and also conceptual physics, but it's applicable here as well. Go ahead and take a look at that second screencast and that lecture on the electromagnetic spectrum now. Okay, now that you've watched those two videos, we can now go ahead and wrap up this lecture in the following manner. And this is also somewhat of a clue for those of you that took physics and honors physics last year as juniors, and also what the last portion of this course is going to cover after the actual AP exam itself. When Maxwell derived the speed of light here, what's not stated in the derivation is the reference frame. What is the reference frame? We'll get to that later. However, before we do, this now concludes the curriculum for AP Physics C. Congratulations, you have made it this far. Today's shirt is Power Trip.